Happy Tuesday. Thursday, we looked at positive series, right? Series with positive terms. Today, we look at alternating series. And just as the name suggests, an alternating series is a series whose terms alternate signs. Right, so you'd either have something like 1 minus 2 plus 3 minus 4 plus 5, right? Or -1 plus 2 minus 3 plus 4 minus 5, so on and so forth. Notice there's no such thing as a series with negative terms. So all you'd have to do is factor out the negative, and then you have a series of positive terms.
Can the series be alternating even if it doesn't follow like every other?
Then it's not said to be alternating.
So if
you could have a series like something like 1 plus 2 plus 3 minus 4 plus 5 plus 6, right? Minus something like that. That is not said to be alternating.
So sine of n isn't alternating?
No. To be alternating, it would have to be every other term switches sign by definition of alternating. Which is funny because we actually write sine of x as an alternating series. But we'll get there. With this is introduced the idea of absolute convergence versus conditional convergence. So this is going to be something you may want to write down on that sheet. So we say that a series converges absolutely, right? Series A sub n, if the series of the absolute value of the terms converges. A series which converges but does not converge absolutely is said to be conditionally convergent, or converges conditionally. There's, I guess, two tests introduced. Really, only one of them is a test. The other one's more of a theorem. If a series is absolutely convergent, then it is convergent. Right? So absolute convergence implies convergence. Alternating series test. If the terms B sub n form a positive decreasing sequence that converges to 0, then the series -1 to the n minus 1 B sub n converges. Keep in mind, this is not an if and only if statement. Right, that means that if the sequence of B sub n is not a positive decreasing sequence that converges to 0, you cannot conclude the series diverges from this test. However, chances are if it doesn't satisfy that hypothesis, then it's probably going to diverge by the divergence test. If we look at this, positive series. If a positive series converges, can we say it's absolutely convergent? Yeah, right. Absolute value of a positive series is just the original series itself. Determine whether the given series converges absolutely, conditionally, or not at all. Right, so now it's not good enough simply to say if it converges. We now need to specify what type of convergence we have, absolute or conditional. Well, the term of our series is -1 to the n plus 1 over n squared plus 1. Notice that n is 1 to infinity. N squared plus 1 will be positive. If you take the absolute value of -1 to the n plus 1, what do you get? It's just 1, right? That term's either going to be plus or minus 1, depending on the value of n. Absolute value of both of them is just 1. Right, that means the absolute value of a sub n is 1 over n squared plus 1. So if we're examining for absolute convergence, we're actually examining the series 1 over n squared plus 1. Does that series converge? Why? So which comparison are you using? Right, so direct 1 over n squared, would that be a larger term? Right? So we do have that 1 over n squared plus 1 is less than or equal to 1 over n squared for n greater than or equal to 1. The series of 1 over n squared is a p-series with p equal to 2, which means it converges. So by comparison, 1 over n squared plus 1, that series has to converge. So our series converges absolutely.
That there's one example. I'm just a little confused. In what case scenario would it converge conditional?
If the series itself converges, but the absolute value does not. So in which case, if you take the absolute value and you get divergent, then you're going to use the alternating series test to determine convergence. So series -1 to the n plus 1 times n over e to the n. Again, absolute value, -1 to the n plus 1 is going to be 1. N goes from 1 to infinity. The absolute value of n is just n. E to the n is never negative. The absolute value of e to the n is just e to the n. We're left with n over e to the n. So to examine for absolute convergence, we're examining the series n over e to the n for convergence. How are we going to do that?
This one, whichever we just used it.
What are the conditions for the integral test? So what has to be satisfied? Right, but there has to be a condition for f of x. Right, f of x has to satisfy certain conditions in order for integral test to be in order for integral test to be valid. And there's one other condition, which is pretty obvious for this case. Has to be positive as well. Well, clearly positive, because we took the absolute value to get it. It's clearly continuous. Right? E to the x can never be 0. Is it decreasing? Well, let's check its derivative. What's the derivative?
These raised to the power of x. The denominator will get bigger and bigger as we go to infinity, so it'll get smaller and smaller.
Right, but so is x.
You can see that then you essentially multiply x by each time, or rather you could multiply x by each time in order to get the same effect, get smaller and
Okay.
smaller. Which I think is enough to make it clear that.
Yes, you can argue that.
decreasing.
You can argue that. I'm just doing this to be safe. Because for on a test, you'd have to make it clear to me that you know why it's decreasing. Something like 1 over n is obviously decreasing, right? That's an easy argument to make. Something like x over e dx is not as simple to argue, but you can argue that way, yes. What is the derivative of x over e to the x? And once it's fully simplified, yes. Critical point, x equals 1. That's nice, since we're only looking at 1 to infinity anyway. That means this function is monotonic. It's either strictly increasing or strictly decreasing over our interval. Right? Because the only critical point is the endpoint. Question is, which one is it? I'll pick any value larger than 1. You're going to get negative, aren't you? So the hypothesis of the integral test is satisfied. This would be an interesting one to do by hand. It's actually not terrible. This would be integration by parts. At first, we write it as x times e to the negative x, just to make it easier. Or formula number 42 on the integration table. Negative quantity x plus 1 times e to the negative x. Like that. Why did I do? Oh, no. Okay, that's right. 1 to b. Should get 2e to the minus 1 minus quantity of b plus 1 times e to the negative b. Well, 2e to the minus 1 is a constant. This limit will converge if and only if that first term converges. Does negative b plus 1 times e to the negative b converge? Why do you say no? Is it times though? Depends. Infinity over infinity is said to be indeterminate.
Well, it looks like if you rearrange the expression a bit, you'd have negative b minus 1 over e to the b, which goes to 0.
Does go to 0. Like that would be either just from observation, realizing that an exponential is increasing much quicker than a linear. So that goes to 0. Or you can use L'Hopital.
But wasn't that basically your original problem that you did all this work for?
Not converging to 0.
Well, yeah, but we were trying to figure.
Something can converge to 0 without being strictly decreasing.
That's true.
It just means at some point it's gonna, well, actually, because it's positive, at some point it's gonna be decreasing. But in order to converge to 0. Doesn't mean it has to be strictly decreasing. That equals 2e to the minus 1. Or 2 over e. So our series or the series we were examining converges by the integral test. Which means our given series converges absolutely. Does you? Absolute value of root n. Just root n, right? Root n's always positive. Anyone take a minute to pause? If instead this series was n equals 0 to infinity, it would diverge. You get -1/0, which is undefined. So you wouldn't even need to do any work. Your work would just be at n equals 0, the term is undefined, so it diverges. That is something important to keep in mind because I have seen some problems throw that in there. If it started n equals 0 instead of n equals 1, right? Because then the 0 term would give you -1/0. So if you have something like 1/n minus 2 from n equals 1 to infinity, that would diverge because at 2 it's undefined. That's just something to keep in mind, right? The terms actually have to be continuous over the interval. Absolute value is 1/√n. For examining absolute convergence, this is the series we're looking at. Does this series converge or diverge? Why? That means our series is not absolutely convergent. However, if we look at the sequence defined by 1/√n, that is going to irritate me to no end. Positive, right? It's also decreasing, isn't it? So it's positive, it's decreasing. Does it converge to 0? It does. So the series does converge by the alternating series test. And so it converges conditionally. Alternating series. Alternating series test states if the sequence B sub n is a positive decreasing sequence that converges to 0, then the series -1 to the n plus 1 times B sub n converges. Right, which makes sense. Even though it's alternating, the magnitude of the terms is getting smaller to 0. So it is going to converge to some value. Right, because you're just adding, subtracting smaller and smaller terms. Right, so there's a case where it did not converge absolutely. One minus a half plus a quarter minus an eighth. So on and so forth. Write this in sigma notation. Did that? That would be a half minus a half plus a half minus a half plus a half minus a half plus a half minus a half. Right, which I'm going to simplify. It's -1/2 all to the n. Which clearly converges y. Hmm? What kind of series is it? And so what type of series has form r to the n? Geometric. This is a geometric series. Converges. Question is it absolutely convergent? If you take the absolute value of -1/2 to the n, isn't that just 1/2 to the n? which is a convergent geometric series. So this does converge absolutely. And in fact, if a geometric series converges, it's going to converge absolutely. That is not difficult to prove. A sub n here would be -1 to the n plus 1 over n cubed plus n squared. We look at the absolute value of that term. Again, keep in mind, we're going n equals 1 to infinity. One over n cubed plus n squared. Looking at the series 1 over n cubed plus n squared. Does that converge? Why? So you're doing direct comparison again. Could also do limit comparison. Doesn't matter. So our series converges absolutely. A sub n term is -1 to the n plus 1 all times n plus 1 over n squared plus 2n. Absolute value would just be n plus 1 over n squared plus 2n, right? Again, because n greater than or equal to 1. We're looking at this series. Does it converge or diverge, and why?
Maybe. Even the, if you're not in anything, every denominator is always going to be. Keep it. You know, the reason why I keep those numbers.
So just because it converges to 0, why does that mean that the series has to converge? I point you to series of 1 over root n. Those terms go to 0, right? But that diverges.
I'd say it diverges because it's very similar to 1 over n. And if you want to actually prove that, you could mess with your index in order to get something like 1 over n plus 2 squared. Well, n plus 2, you know what I mean. And then remove the first terms and then show that that series, which is either both of them are convergent or both are divergent, and show that that one's always greater than 1 over n. I mean, yeah, greater. Or something like that.
You did way too much to get to that. You could also use limit comparison with 1 over n. Divide that whole thing by 1 over n, the limit would be 1. But here's what you're trying to get at, right? Just factor an n out from the denominator. Oh, wait, can I actually say that's always larger than 1 over n, though?
Well, no, but I was thinking you'd have to mess with your index to get some extra.
Actually, I think I do have to do limit comparison here. Yeah, because n plus 1 over n plus 2 is less than 1. Yeah, I can't just say that's always greater than or equal to 1 over n. That's what I was hoping I could do, but I can't. I'm going to leave that there, though. Right, yes, you could try and mess with the index. But again, that's just doing way too much work.
I mean, it's pretty clear that you can add anything, like any well, any integer to all the n's
Right.
while keeping the index the same, because that's essentially what messing with the index and then dropping the terms does, which allows you a lot more freedom.
Again, true, but that's more work than limit comparison. As my boss used to say, work smart, not hard. Get paid by the hour, regardless of how hard you work. So work less, get paid the same. That limit is 1. Remember, there were 3 possibilities. Greater than 0 but finite, which is always the case we want. Equal to 0, or infinite. Well, 1 is finite and greater than 0. That is the if and only if statement. Numerator converges if and only if denominator converges. Harmonic series always diverges. So we're comparing it with the harmonic. So our series diverges by limit comparison, which means the original series does not converge absolutely. But if we look at that sequence of terms, that is a positive decreasing sequence, right? And what's that limit? It was set already. The limit is 0. Which means our series converges by the alternating series test. Meaning it converges conditionally. Very easy to see it's decreasing. Because you have a term less than 1 times a term less than 1. Which is smaller. And it's always getting smaller. Here. Since we're starting 1 going to infinity, n squared over n cubed plus 1 is always positive. Testing for absolute convergence, we want to look at this series. Does that converge or diverge? Why do you say converge? What's your reasoning? Well, that's not alternating, is it? I'm not looking at the original series. And test for absolute convergence. Hmm?
Well, you get a harmonic which always diverges. But I don't know.
Well, that doesn't tell you anything. Other than maybe what to do.
You want to do limit convergence, I mean, limit comparison test
To what?
to 1/n.
I'd write it that way. That limit's 1, right? Our comparison series was that. So it does not converge absolutely. But the sequence defined by n squared over n cubed plus 1, definitely positive. Certainly decreasing. And again, that's not difficult to show. And it converges to 0. So that series converges by the alternating series test. And so it converges conditionally. Series n equals 1 to infinity, sine of n over n squared plus 2.
It's convergent by direct comparison with 1 over n squared. Actually, wait, the sine of n can be negative. Which, well, if you took the absolute value, that would be conversion, which means this has to be conversion by alternating series test.
By what test?
Alternating series test. Well, I guess this isn't an alternating series, but
Right. It's not alternating, so you can't use that. You can't use direct comparison because it's not always positive. The limit is, yeah, the limit is 0. Which is a bummer. So here, examine this series. N squared plus 1, always positive, so we don't need the absolute values. Isn't that less than or equal to 1 over n squared plus 1? Because the absolute value of sine is always less than or equal to 1. But that itself is less than or equal to 1 over n squared. So you are on the right track with direct comparison. You just have to look at the absolute value. So the absolute value, right, series of the absolute value of the terms converges. By comparison. Which means the series has to converge. Because absolute convergence implies convergence. This gives us a way now to look at certain series that involve sines and cosines. Are there any questions?
Is the quiz gonna be within the next, like, 2 minutes?
I'm about to give it.
Okay.
We have two tests left to look at. Ratio and root. Which are the most powerful tests? We look at those on Thursday. You're welcome.